Welcome to In the Open with Luke and Joe. I'm your host, Luke Shantz, and here's my co-host, Joeseph, and a big welcome to our special guests, Liz Joeseph and PJ Catalano. Before we get to our show, don't forget to like and subscribe. In this episode of In the Open, we bring you a conversation with Liz Joeseph and PJ Catalano. Liz is a Linux systems engineer and developer advocate for IBM Z, and PJ is a senior technical staff member who specializes in mainframe hardware testing. Before we welcome our guests, let's say hello to my co-host, Joeseph.
Hey, Luke. How are you, my friend?
I'm good. How are you doing, Joe?
I'm okay. There's a lot going on, as you know, like selling and buying houses and stuff like that. It's driving me crazy, but things are good. So that's good. And the weather's been nice, got the pool going and out in the yard. Good stuff happening. How about you?
Well, I'm glad you're selling your home now because I hear the market may slow down. That's what I didn't read the article. I just read a headline, which is enough. Sometimes that's the impression I get. I would mention that we had a bit of a heat wave last week. We had some like August temperatures in May. It was like seriously hot. My dashboard thermometer was showing 99 degrees. It was very hot.
We were silly. My son and I and a friend went mountain biking in peak heat for like 3 hours and almost didn't make it home. It was hot.
I had a minor heat stroke doing some yard work. I definitely did.
Yeah.
Anyway, without further ado, let's see how the weather is with our guests. Hello, Elizabeth, and hello, PJ. Welcome.
Hello.
Hey.
So let's start off with you, Liz. How are you doing today, and how's the weather where you're at?
I'm great. And I live in Northern California, like right outside of San Francisco. So it's always beautiful here. So it's sunny, 70 degrees. It's good.
Excellent. Nice.
And PJ, how about you? How's the weather where you're at?
Yeah, here in the Hudson Valley, New York, it's actually about 74 degrees, but it is really humid. So yeah, it was brutal last week. I agree, Luke. It was in the 90s, and I'm like, I wish my pool was open, but we're not there yet. Hopefully this weekend.
Yeah, the dry heat thing is no joke. Like moving out west, like it's not humid, and it's glorious.
Yeah,
I'm jealous.
Great. Yeah. And so, PJ, you're in the Hudson Valley. Liz, I think you had said before we went on the air that you were in New York, but you moved out west.
I was in Philadelphia, yeah, and then I moved out to California. We still have a place there, so sometimes I crash there and then go hang out with the guys up in Poughkeepsie. So.
Nice. Yeah, that's what I was going to ask about. We Luke and I got to go visit the shop up in Poughkeepsie, and that was really fun.
Fun place to be. Absolutely.
Yeah.
I was amazed by the sort of the manufacturing floor and like how, I mean, we're going to dig into it here, but it is really impressive hardware that is created there. Fantastic stuff.
Yeah, it's a serious operation, the manufacturing floor, and we have the test floor as well, right, which is another big operation. So we have lots of hardware to play with and touch, and next time you guys are out, you got to make sure we visit the test floor.
Yeah, that'd be great. It's funny too. I've been at IBM, I think actually almost 6 years now. But before I joined IBM, I think I just thought that like mainframes were a thing of the past. Like I was like, what do you mean? Okay, mainframes, cool. So yeah, I just think it's interesting. Like I wonder how many folks in the world, especially people who are working in the computer field, like think that mainframes are history.
Yeah, I mean that's the impression I had. So I joined IBM about 3 years ago, and I'd been working in distributed systems. Like I was at a container startup in San Francisco. Before that, I was working on OpenStack, the open source project for distributed computing. And like when IBM was like, "Hey, you want to come work on mainframes?" I'm like, I don't think so. But then, thankfully, they set me up with to talk to some of their technical folks, and they're like, "No, Liz, this is really cool stuff."
Yeah.
But like it's funny because like I look at the dialogue even still like in my with my friends over on the cloud native side, and they really have no idea what it's like. I discovered this whole secret place that is like the mainframe community and enterprise computing. Like they're real things, and they're really cool.
And they're really important to everything we do, right? From financials, stock trading, credit card transactions, medical, like everything touches a mainframe, right? And so I've been IBM almost 20 years now, and I started a mainframe. So like there's other computers in the world that are important? Not really. It's a mainframe. That's where it's at. And just seeing the technology evolve, right? Even in the last 20 years, and kind of how the platforms kind of broaden, beyond just the traditional transaction processing that kind of the mainframe's known for, and kind of getting into, more specialty processors and optimizing around Linux and growing into the Linux market. It's been phenomenal to watch, right? Because it's seen as this big refrigerator, right, that sits on your data center. But the transformation of kind of this specialized Z footprint that, only we fit into it, 24-inch frame. Nobody had 24-inch frame space. And kind of over the last couple of generations, getting to the standard 19-inch rack frame, right? We kind of fit now more nicely into data centers, and kind of can, start branching out. And really that transition, we've seen a big uptick in people that weren't as interested or knew about the mainframe starting to now show interest, which is fantastic to see.
Yeah, I would have to mirror this whole thing. Like I had no idea, but after spending, I think it's about 6 years at IBM and meeting a lot of, experts in the space, I've come to realize that like the mainframe is like a cornerstone of modern civilization. Like the planes would drop out of the sky, your health records wouldn't be there, you wouldn't be able to use your credit card, and there really isn't another like comparable solution, right? Like the thing, and it's funny where you mentioned like web dev, someone said earlier, it's like I feel like this, whatever space you're in, you kind of feel like that's the whole world, right? So it's like you hang out in the JavaScript world, it's like who cares about mainframes? And then you go, if you're a crypto developer, you're like, oh, it's all about Web3, and you realize that like no, that there are layers to this, right? Like and mainframe is like cornerstone of modern civilization.
Yeah, and I wonder why is that? Tell me why mainframes just don't go away? Why nothing's replaced them? Why is that?
I mean, we could even back up a moment, and for anyone who's not aware and hasn't been at IBM for 6 years, essentially what they are, like we mentioned, they fit into like a 19-inch rack spot, but like they fill the whole thing. Like it's a box, and it goes in that spot. But the big thing is that it's pretty much all just processor and memory and IO cards. Like it doesn't like it's you think of like a 1U like server rack mount system or something, and that's got like your hard drive and your processor, and like everything it needs to be a computer is like contained in that little tiny box. But with a mainframe, it's actually just a component of your bigger infrastructure. So like your data is on one machine, your processing and IO handling, and like for that, and the memory and everything is on the mainframe. And so that's what that big black box is. And one of the reasons that it is like the cornerstone of all of this data that we're processing in these really important organizations is because like that's what they were built for. Like if you think of the first industries that ever needed computers, it was because they were doing math, like putting people on the moon, and because they were storing data. So like customer records were like a huge thing, early on. And of course, things like medical records and tracking flights and tracking passengers. And I think one of the things is like the processors themselves, because it's a different architecture hardware wise than something like x86 that you may be more familiar with. But even the CPU is designed to process lots of data really, really fast. And so like the whole point of a mainframe is really fast data processing. Everything's been optimized for that. And I think in other realms and in other infrastructure organizations, like maybe data is not the thing they need to be fast. Maybe they're a web shop and they need networking to be fast. And it's just because it was specialized to do this, it continues to excel at that.
Yeah, and the other thing to add on is it is highly reliable platform, right? We understand the importance we play in many of our customer shops. Your mainframe can't go out to lunch and everybody's okay with that, right? fully redundant systems throughout, right? The availability of the system, we target 7.9 availability, right? So 99.99999%, right, uptime. And the other thing it's designed to do is, even if there is a component failure, we can service that thing, replace the component without taking down the system. Fully concurrent, right? So customers have built their business around this reliable backbone. And as you said, there's really nothing else in the industry that does what a mainframe can do.
Yeah, and it's funny because you mentioned 7 nines, but like in the industry, if you're talking infrastructure, 5 nines is like the goal. That's what every infrastructure org, and that's what, all of them will brag at. We're like, we have 5 nines. And I come to, IBM Z systems and they're like, we have 7 nines. I'm like, that's not a thing.
Yeah.
That's amazing. Yeah, I think in like when we're leading up to this in the prep call, somebody said something like a 20-year uptime, or I don't know if that's real or what, but like, I mean, that's the whole point, huh?
Yep. Yeah. I mean, the Z and Z systems is for zero downtime, right? And that's really what we're striving for every product we ship and deliver and support in the field is. And again, it's because we understand the importance of why the industry and the clients use our platform, and we want to be there. We're partners with them, right? They can't stand to be down a second, no less hours or multiple hours. And they want to, have backbones they can rely on. And that's really where our footprint is, our staple has been. But, we also bring kind of cool, neat features as well, right? And kind of the monetization is bringing more AI onto the platform, doing kind of inference processing kind of at the time of transaction, right? And really kind of bringing features and functions that we've kind of co-created with our partners, right? Our customers, of saying, what do you need to make your business better, right? And kind of Z16 and as Liz saying, the new Telum processors bringing a lot of that AI and interesting learning, at the time of transaction, not I have to move that data somewhere else to do that. Because in our world, if it takes 2 seconds for your app to load, you're closed and you move into the next app, right? So when you swipe your credit card, you don't want to be standing there for at the counter for minutes while the bank company is trying to figure out, is this real? Is this, is this fraud, right? That's gonna time out, and they're gonna go pull another credit card out from another bank and swipe that instead, right? So the speed that we've expect of our world, right, and everything, has just kind of increased, right? And customers want that, right? So our customers want to serve their customers and give them the best of breed product that can do that while also protecting their core business.
Yeah, and I don't want to get too like IBM salesy here, but the other component, of course, is security. So like we do this all, and then it's like all secure. But that's actually where we get into some of the really cool hardware stuff too. So we can talk about that too.
I'd like to mention, if anybody has any questions for PJ or Liz, please feel free to drop them in the chat. We'll get to them. And if you're watching this after the fact, you can see we have all of our Twitter handles up here. Feel free to tweet at us. We're happy to answer questions. And I would also just mention there is, if after you're done watching this, then check this out. But there was a Linus Tech Tips video that I know PJ helped out on that gives a tour, and he's playing with the thing, and he'll show you all of the, Liz was mentioning the rack and how things are connected and getting into what these things look like. So I would highly recommend this IBM Z tour video. Would be really interesting. I watched it recently myself, and it was a lot of fun.
Yeah, and it was a lot of fun making that video too.
Tell us about it. How did it happen, and what was going on?
Yeah, so the IBM's comm team reached out to me earlier in the year and said, "Hey, have you ever heard?" It said, "We have this YouTuber who's interested in coming. Would you be, interested in working with them and give them a tour of the test floor?" I'm like, "Yeah, sure." I'm like, "Who?" They're like, "I don't know, like Linus guy." I'm like, "Wait, what? Like Linus Tech Tips?" Like, "Yeah, that's the guy." I'm like, "That's the guy?" So I'm like, yeah, can you just give him like a hour tour of the test floor? He's like, he was going to come to Poughkeepsie. We were going to spend the morning with him, give him a tour of the test floor, talk about the mainframe. He was then going to go off to look at some of the other labs we had in Poughkeepsie. We have compliance labs that do shock and vibration testing, acoustic lab, right? So he was going to do a tour in the afternoon. So, we're talking, we're planning, and the day arrives, he shows up, and it's like, all right, PJ, he's all yours. I'm like, what do you mean, oh my? He's like, yeah, just like, you're going to lead this whole thing for the day, right? I'm like, I am? I was like, I thought I was just giving this guy a tour. We dumped on Linus for 5 to 6 hours straight. He knew nothing about the mainframe, right? And we had some technical experts there talking about the processor, talking about the AI stuff I was mentioning. And, I'm a hardware guy. We're showing him the floor, showing him all the cool stuff. And he's like, yeah, can I just start ripping cards and power cords out of this thing? And I'm like, and I'm thinking like, did we finish all the testing on that stuff yet? I'm like, concerned where we are because we were actively still testing, the product as we're going. I'm like, yeah, I think we can make that happen. So we had our team lined up, and yeah, he spent the whole day. Now, it was pretty obvious, like in the first 3 hours, like he did not want to leave the test floor. So he's like, yeah, he's like, what am I supposed to do in the afternoon? He's like, yeah, I'm not interested in this. I'm just going to stay here all day. And we made it happen, right? And I think one of the coolest parts is, when Linus actually went over and we had him plug, the DCMs, the dual chip modules with the Telum processors into the drawer. And Arvin came to visit. We wouldn't even let Arvin touch the drawer in the chips, but I knew, from watching, Linus's videos, like this is what he does. This is what his audience wants to see. Like we need to make this happen. So I didn't tell the team that, owns the drawers and the configuration that, I was like, oh, we're going to show Linus the drawer. You're going to model how you plug the chip. And when he's heading over, I'm like, so he's going to do this now. And they're like, oh, no. I'm like, oh, yes. It's like, we're going to make this happen. And he did it. We taught him how to plug the chip. He did a phenomenal job, right, explaining it. Some of the stuff he was explaining better than I did. And he only known the thing for, 5 hours. But it was it's one of those days where I don't have many of these in the career where like I remember the whole day from start to finish, right? It's like I will treasure that time in my memory. But it was a phenomenal experience. And the way he picked up on what we were talking about, the use cases, the technology, phenomenal, right? And I think it turned into a pretty neat video. And I got the cameo in it a little bit.
Yeah, it's a great video, and to see him go through all the stuff and to interact with you and other folks off screen, and it was a good video. I enjoyed it. Yeah,
and it's amazing space, our test floor, right? I mean, it's about 80,000 square feet. We have 200 mainframes. We basically run the power of a small city every day. And the reason we do that is because there's these platforms have become so complex. We need to have, different configurations, teams focused on different areas and testing it. Otherwise, we would never get through a test cycle, if we didn't have that many mainframes, within a reasonable amount of time. So, and it's great, right? And you could talk about 200 mainframes until you see 200 mainframes in person. Like you don't understand what it's like. It's a number, but you walk in and you just see the awe of people's faces when they walk in, and great place to work every day.
Yeah, it's impressive. Very cool. Yeah, and I think that's the floor that Luke and I were on, and a gentleman pulled out a sheet, like a spec sheet for the one that he was putting together, and can't remember what bank or whoever it was for, but this one's, let me see, this one's about $3 million, and just like it's amazing.
Yeah, these are serious hardware, serious systems, right? They can be expensive, but there's all different pricing models. So like people often ask me like, how much is a mainframe? It's like it depends. Like you could have a 1-frame system, you could have a 4-frame system, right? I mean the scale, and we build, and these are not like off the sitting on a shelf somewhere, right? All these are custom built, right, specifically for customer needs, right? And, we customize them and make sure it fits whatever availability requirements, reliability requirements. And then the manufacturing team does a phenomenal job building these things and getting them out. And we're going to start shipping our first Z16s Tuesday. So I'm really excited for these to actually get in our clients' hands.
You're on mute, Luke.
I was muted.
Yeah.
We have a comment from one of our IBM champions. Such a great story, PJ. Awesome to hear some of the behind the scenes. First time he's been able to tell people what he does because he works with mainframes as well by sharing that video. So thanks for tuning in, Stephen. We were on a stream recently together during Think, so thanks for checking it out. And also, he's in the same world, so he gets it. Like trying to explain to people what you do sometimes is difficult, but the word's getting out.
Right. I mean, when I explain to my mother what I do, I'm like, I work on computers. That's about the level of depth, right? We can get, and this at least people like, oh, that's what those things do. I'm like, yeah, this is what it does, right? And to be able to articulate that, because to me, I'm a tech nerd. Try to explain something to someone, like you want to get into the details and tell people how awesome it is, right? And you just lose them, right? You just see their eyes glaze over. But yeah, I think the video is a great, 10, 12-minute snippet into the world of mainframes, right? Without kind of getting drowned by all the cool technology.
Yeah. And you, one of you two have mentioned putting people into space. Is that sort of when the mainframe started? I mean, I saw the movie, now I'm forgetting the name of it. But somebody will know. Yeah, which is a fantastic movie. We lost Elizabeth. And I'm sure she'll join back in. And I've seen photos of there are the rows of the NASA jackets on the back of the chairs, and then there's another photo of a row of IBM jackets on the back of the chairs. Like those, room-sized computers. Is that where the sort of mainframe started, or is it, what's sort of the backstory there?
Yeah, so I'm not going to claim to be a mainframe historian, but yeah, I mean, it all started with the basic computers, right? I mean, business technology and business machines is what we do, and it's how do you process things quickly, right? And yeah, full size rooms of computers with people working on them. That's kind of the birth of the mainframe, right? We thank goodness we don't take up full rooms anymore, right? Yeah, I mean, it's been computational, right? And transactional processing was kind of where mainframe was born, right? And you could think of, calculating, launch, the power we have in our cell phones, right, today versus the computers back then, right? You could probably calculate launches on your cell phone, no problem. But the math processing back then obviously was really the foundation, right? And the birth of kind of the enterprise computing, right? And the design, right, of, well, how do you design compute systems that survive in space? They have to be highly reliable, highly available. Those things can't go, right? Those are systems that need to be functional because people's lives are at stake, right? Yeah. And you can trace kind of our roots kind of back to those, early NASA missions, right, of the technology, right? And how it then grew into, and like all modern technology is like, usually it starts with some space exploration thing and then it becomes consumerized, right? So, that enterprise market kind of built off that foundation of the technology they had to develop to keep astronauts alive, right? Now, businesses are using to rely on, right, to keep their businesses running.
That's really interesting point too, just to think about, sometimes you wonder about like, oh, should we spend money on that space project? And it's like, well, there's other things that happen from, it's like doing your homework or your test. Like, yeah, you may never solve that problem again, but you'll be able to solve these 20 other problems because you solved that problem.
Right.
And you mentioned the space isn't like, I think most of the chips on a lot of the rovers and these things are all IBM power chips is a common chip used in the space rovers, I've heard.
That's very possible. There was a one time, to me, that's not as interesting as one time IBM made like all the chips that went into the video game consoles, right? We had the PlayStation 3, the Nintendo Wii, right? I mean, we did the Xbox, right? So that's cooler to me because that's like, oh, we're technology people can actually touch and understand. And that's, some time ago. But yeah, our chips and our chip design, I mean, I think with the, we have in Albany, the Nanotech Foundry and Education Research Center, right, where we're developing things like 2 nanometer technology. I still think IBM's still best of breed of developing kind of the new core technologies that go into making, the chips that go into everything, right? And yeah, it's definitely a keystone of what we do.
So I was going to ask, you had mentioned testing earlier, PJ,
yeah.
And I'd like to understand a little bit more about like and I listened to a podcast you were in. You were talking about this N-1 testing.
Yeah,
and I feel like it's such an interesting concept. Maybe you could tell us a little bit about that.
Sure, absolutely. And you know, it takes a village to test the mainframe, right? As I mentioned, these are highly complex systems. So one of the focus areas we were looking on, and we do it every platform, but we did it especially for Z16, is, you know, what can we do better to have a better quality product, right? And one of the things we started looking at is what's some innovation we can do, you know, broad scale that would actually pay dividends, right? Once we kind of get started on Z16. So we started looking at kind of what some of the smaller development teams were doing, where they were taking kind of their next generation IO cards, and then within their little test environment, running special little code to make it work on the previous generation platform. So for example, like making it work on Z15. And we said, that's really neat, right? We have like 6 brand new next gen IO adapters on Z16. How do we run a program at scale, right, to test this? So we called it N-1, N being the newest generation of system, N-1 being the previous one. In this case, that was Z15. So what we were able to do is build a specialty test driver that we could run on Z15 that would allow us to run these new IO cards, right? And we're talking about Ficon adapters, fiber channel adapters for storage attach, you know, 25 gig, OSA and Rocky, right, for Ethernet attach, new coupling links, new crypto cards, and get them to work. And we did a full test cycle, about 6-7 months worth of testing just on the IO cards. Now, that generally will run in parallel with the kind of our final system test of the system, which is about a 9 to 10 month effort. So to be able to pre-test a lot of that hardware to make sure the hardware is solid and make sure the firmware on those cards is solid, once we got the real hardware for Z16, because the Z16 processors didn't even exist at that time, right? So once we got the processors and built the systems, we could plug these cards in and know, you know, we have some high level of confidence that kind of we could focus our attention on the new things like the Telum processor, right? Like how the i390, which is our special architecture sauce, right? That kind of defines what Z is, interacts, right, with the processor, with the IO infrastructure and subsystems, right? And really bought us a running head start in terms of quality to starting this whole test cycle. So the amount of effort we put into making sure and, you know, again, we were talking like teams of like 5 to 6 people running it, and we scaled it to the entire hardware firmware test organization, which is I have 100 testers on our team. And then the whole development team and infrastructure to build these drivers, deliver us code on these drivers, right? So it was a big investment, and it really did pay off, right? We could draw straight lines from, hey, look, this test case, and we track ourselves using metrics like run rate. Like, this is a test case. It takes me 4 times to run that test case before I could sign it off, right? We have straight lines that said, look, it took me 1.5 times to run it this time because we ran that test case in this N-1 cycle. You know, again, there's stuff we have to sort out and make sure it works in the back end, but it gave it really going to pay off in terms of quality.
Yeah, and what I love about this story is, in general, it's just you don't have the hardware yet. Like, you maybe have a little tiny, you have like one piece of the hardware. And I think this is one of the things that I love so much about technology is, like, you're doing like really hardcore like hardware work, but you also have to be so creative. And like the answers aren't necessarily there. Like, they're like, here's your new IO card that you have to test with the new system. And you're like, but I don't have the new system. And now you have to like bootstrap that and figure out a way to do tests that are going to be effective. And I think that's that kind of creativity is something that's lost, I think, a lot on a lot of people who think about technology, but like there's so much you have to do to literally think outside the box, because the Z16 box not here yet.
There was no box to even think about it, and so and you know, and there's different levels of effort it takes to make these adapters work. So for things like storage attachment, which is Ficon and fiber channel, mainly for the enterprise market, that's fairly easy, right? Generally, it's just, hey, it's a speed increment, right? There's some new technology on the chip. That's good. But when we talk about like coupling adapters, now coupling is kind of a staple to Z systems, right? And that's the technology that we use to interconnect our systems to run these big complex sysplexes, which is just a fancy word for, hey, a bunch of partitions of operating systems that are well coordinated, right, and understand who's in control and who could write the different data structures. But that coupling technology is so integral to how the system works, right? Making that work on an N-1, because it is completely different, right? If we're looking at a Z16 versus Z15, that is a huge amount of effort. So what we had to do is have kind of these different levels of drivers that ran different cards, right? And, you know, again, the more fuzzy we try to make that Z15 look like a Z16, right? The more instability, I'll call it. Again, these are not drivers we would ever ship to a client. These are just test drivers. So, you know, dealing with the understanding of, okay, this kind of behaves how we think it's going to behave, but it's not 100% hardened like we would for, you know, testing on a full test cycle, and understanding what trade-offs and what we should go after, right? That it's a feat of engineering just to make that happen. And that's just for a test effort, right? That's not for the actual technology itself. And yeah, a lot of great work.
Yeah, that's fascinating. This is the talk that references that, a time machine for testing?
Yeah.
Is that right?
Yeah, it's a little Terminal Talk podcast where we go into a little bit more detail on how all that magic happened.
Great. Yeah, that's fascinating. So for folks who want to dig further into a time machine for testing, which sounds pretty magical, definitely check that out. And speaking of magical, because I find this technology really magical, I think most people do. And it's interesting in this context because we're talking about mainframes, right? And this sort of foundational aspect with historical, aspects as well. But we were talking in the prep call about quantum safe encryption. So like bleeding edge sort of stuff, but, super important as well. Liz, can you tell me why we're thinking about that sort of stuff in the mainframe?
Yeah. So for folks who aren't aware, quantum computers exist. They're even like IBM has ones that are publicly accessible. So there's some like SDKs already out there, so you can play around with them. But they're not at a point where like you can use them for like some of the things we think people will be using them for in the future. There's a lot of just development work going on right now. But the one thing that we know quantum computers are going to be really good at is encryption. And that is in some cases breaking encryption. And that's really what the whole quantum safe narrative is around. It's like, it's at some point, the quantum computers will be here, people will be using them, and the encryption algorithms that we have out there, they won't be strong enough anymore to resist the quantum computers. And so there's a lot of research happening right now, both inside of IBM research and then like at organizations like in the US, like NIST, that are doing research into finding stronger algorithms that are quantum resistant or quantum safe, and then just using larger key sizes when you're doing encryption. And the big thing there is that doing encryption is very resource intensive. It's something you need a lot of CPU for. It's something I didn't think about when I built my at-home media server and we got really, really small CPUs. I'm like, it's just a media server. And then we encrypted the hard drive and we realized that we did not have processors that were strong enough. So like that's my house. Think about, when you have a mainframe, like one of the great things is like, these systems can have like 200 CPUs in them, right? Like in like a fully decked out one. And so and it also has a crypto coprocessor for storing keys. There's a crypto express card that handles like, it's a HSM, a hardware security module. And so what the Z16 does is it not only like can support all of those really, really strong keys, like the better algorithms, the longer keys, but like, yeah, so it can support those. But we also have like detection software. So it can like go through your whole infrastructure and like find weak keys. Like they're like, oh, this key is not very long. You should use a longer one. And also detect weaker algorithms, the ones that are identified as not quantum safe. So that's kind of the idea there. It's just that like mainframes, they're fast, lots of processing power. So we can do really, really good encryption, which is going to save us from this quantum threat. And it's funny because we're saving ourselves from the threat that we're also creating because we're making quantum computers. But it's real. And like the one use case they like to throw out there is like, people are harvesting personal data right now, and maybe it's encrypted. But if they sit on that data for a few years, maybe they'll get a hold of a quantum computer, and then they can get a hold of that data. Even if it's a few years old, it may still be valuable. Like my social security number hasn't changed much, so it's still going to be valid in 5 years, chances are. So like there is data that's already being stolen with the intent of decrypting it once that's possible. And it's already happened to some extent with classic computing, because as computers get faster, older crypto algorithms that were fine in like 2003, we're like, don't use those ever again, because you can crack them in like 3 seconds. And so that's really where the quantum safe stuff comes about.
And you think about hacking, and people might think, oh, well, some guy, or group, rogue group or whatever, they're not going to get a quantum computer. It's far off. But there are state actors and stuff, right? That actually their governments are working on quantum computers. And so I imagine it's a very real threat, and maybe even not that far off. Is this something distant in the future, or you think it's actually, I guess you were just saying, with some of the older encryption, it's current.
Yeah, as I say, some of this has already happened. I don't know the timeline for quantum computing. The IBM research guys have really good. They just released a new roadmap for all of their stuff, but I don't know about that stuff. But it's very real. We've known about encryption problems for a long time. It's just gonna.
And I think one of the things is people ask me is oh, is quantum safe like an IBM made up term? It's no, this is an industry standard term, right? And there's 60 or so algorithms that were submitted to NIST and ETSI. I think it's ETSI, the other one, the European one that that they're going through, and they're down to 7 or 8 algorithms that they actually think are going to hold up against this, and they're going to pick a handful that said these are them, right? And the point is we're ready, whatever the one it is they pick, we're ready to turn that on, right, in our hardware today, to kind of lock down that data, right, so it can never be. And encryption and quantum safe encryption, there's lots of different encryption on the platform. So you're encrypting encrypted stuff, right? And we want to make sure, right, that again, data breaches are expensive, right? And bad publicity. So anything clients are interested in turning more keys on to keep it safe, right? We encrypt everything that leaves the box, right? We encrypt things that stay on the box, that never leave the box. We encrypt things at the storage unit, right? So when it's at rest, it's encrypted. So it's a hot topic, right? And people are not only using encryption to protect against, outside threats, right? They're also using it to protect against inside threats, right? Where, love to use the Snowden case, where somebody who had access to the data center and the data, could just go and make a backup copy, right? USB to themselves and then walk out with it, right? They want to make sure nobody could use it. And some of the things we're looking at moving forward, right, is around this fully homomorphic encryption, where you can do analytics processing on data without ever decrypting it, right? And that's kind of some of the future stuff that we're looking at. But yeah, it's anytime you put that data in the clear, there's some risk someone could see it or grab it. So why take that risk? And it's some amazing technology, right, that the research team's coming up with to make that happen, right? It's how do you transform and manipulate data that you don't even know what it is, right? They're going to figure it out.
Yeah, and one of the things I was really interested to learn was that there's the hardware component, which is of course the silicon. You can't really change that once you ship it, but there's also a firmware component to the CPU, and that can actually be updated. So this actually came up in with regard to the AI accelerator, which is also new on this chip, but being able to even after you ship something to be oh, here we can support crypto, even better because we're going to ship some new firmware. That was really cool because you don't just have a static machine. It's really something that can be updated even after it ships.
Yeah. And the other neat thing is we're making more and more of this cryptography available, through the cloud too, right? We're using the HyperProtect program, right, where hey, look, there's new, again, algorithms and standards that are coming out, quarterly from these organizations that, customers want to be compliant with, right? So we need to be able to deliver those algorithms on our current systems as well as future systems, right? So not only could they use with the data they have today, but also, decrypt it when they move forward in time, right, with the new system. So the whole crypto space is amazing in terms of how rapidly evolving that is, and at the speed at which it's changing. Because I think it's a big risk concern, right? And enterprise clients, right, especially, they're very, I wouldn't say risk adverse, but they go to no stop to mitigate risk, right? Because again, and we talked about this earlier, this is the backbone of their business. This is their most important data that's getting processed here, right? They do not want anyone to have that, because someone has their data or their operations, then they might as well give their business away to someone else, right? So that's why having this, the latest and greatest, being able to change, and if there's a breach, or this algorithm's no longer good because it's been cracked, we could change it, right, for at the client site, and they could pick and choose which ones they use, right, to whatever fits their risk profile.
Yeah, and that's one of the things I love about the hyper protect services is they don't talk a lot about what the technology is behind them, because it's it's just it's very secure, I assure you. And then I'm like, no, let me tell you, the crypto services that we provide, I think it's actually called hyper protect crypto services. I think it's the key service. And not only do you have assurance from IBM being I assure you this is very secure, no, we can tell you that your key is actually going on to physical hardware, the physical HSM in the IBM Z system, and that has been certified as tamper resistant, and even IBM can't get at those keys if we don't have the private key, right? So I love that there's this connection to actual physical hardware, even though we talk about clouds and we kind of think of them as somewhere around, but no, IBM has mainframes in our data center, and that's what we use to store your keys when you're using something like HyperProtect.
So I'm curious, and there was something kind of like a question around this in the comments, but as an everyday developer, wondering about mainframes and curious about it, what can developers do now to interact with mainframes, or I don't know, learn more, or somehow go on that path towards being some sort of mainframe engineer, I guess?
Yeah, that's a good question. So there's a couple of paths you can take when you get into the mainframe space. And I like to divide them into two because that simplifies things. I kind of say there's the Linux side, which is where I come from. I did Linux my entire career before joining IBM. So Linux has been running on mainframe for over 20 years. And so that's one side of things. And that's where a lot of microservices and containers and things come into play. But then there's ZOS. And other proprietary IBM operating systems, but let's just call it ZOS for simplicity. And that's where you find all of the really hardcore, old school, but even new students who are coming in and learning about mainframe. ZOS is where all the that sort of traditional data-driven workloads go. And so if you wanted to learn about that side of things, which is very, it's a very different type of computing than I was used to in, the past 15 years of my career. When I first got in a login, I'm like, okay, where's the file system? And they're like, well, it's not really like that. You're dealing with data sets and you're dealing with processing of those data sets, but you don't necessarily put a file in a spot and then, touch it later. It's just a very different world. So the ZOS side. So one of the ways that you can start learning with that is there's a IBM Z Explore program, which is a learning platform. I don't know if I gave you guys the link earlier, but we'll make sure it shows up, I don't know, show notes or something. And so that's we also launch a student competition in the fall, but this learning center is open all year round. You can go onto it. There's a bunch of exercises. You progress through, hey, we got a link. We progress through challenges. There's also a Linux component. And it's really cool because you get to learn a lot of the fundamentals. And then from there, you can figure out what was interesting to you because there are dozens of jobs, probably more than that, in the mainframe space. Once you start digging into it, you learn there's all these different roles and not everyone knows everyone's pieces. You really have to start specializing at that point. But Explorer is a really good place to start. On the Linux side, the really good thing about working on Linux on Z is that it's pretty straightforward. I got my first VM and I was like, I have Linux on a mainframe, woo! but it's just Linux. Like it's, I can type ls, I can, run a web server. And so it was somewhat anticlimactic because Linux is Linux, but that's also the point. Like we want people to be able to share workloads between, whatever cloud system they have, and then come back to their Z system and then go back to another part of the cloud, and just be able to move those Linux workloads around as they need to and as makes sense. And so the Linux side of things, it's honestly, you can just grab any random tutorial and just run it on a Z system. And we have a Linux One community cloud, which gives you free accounts for I think it's 60 days, and you can renew it for 120 days total. But this gives you a Linux VM. You can choose between Ubuntu and Red Hat and SUSE. But you can just really play around with that. We'll shut you down if you start Bitcoin mining or something, but we have things to track nefarious activities. But yeah, we got a link here. So that's the Linux One Community Cloud. And also, if you're an open source project, we do give permanent VMs as well in a different part of our data center, where we grant you an allocation of VMs that you can use in your CI system or whatever if you want to release binaries for your open source project. And so that's what I spend a lot of time on, is just interacting with open source projects directly and giving them Linux VMs. And I'm like, come on, build for S390X. Let's go.
Yeah, I work in the Node community, and we have some ZOS stuff that's running. I don't know a lot about it, but I know the guy on the Node side that manages that. It's really fascinating.
Yeah, and it's funny because every time you talk about a technology, you said Node, and I was thinking about Linux, but you're actually talking about Node on ZOS, and they're just so different because ZOS is a very different operating system than something like Linux. So so Node is supported on ZOS. Of course, it's also on Linux. So there's a lot of languages like that are you first have to specify wait, are you talking about Python on ZOS or Python on Linux on Z systems?
And there are a bunch of third party Z system certifications out there as well, right? So yeah, there's a ton of education. Definitely recommend starting with these two places to kind of get your feet wet.
So you had mentioned earlier, Liz, about how the mainframe was set up, and PJ, this is a question for both of you, so feel free to chime in because I know you know about this because I watched the Linus Tech video. But you had mentioned how sort of when I look at my laptop, it's sort of set up to, the processor's here, the RAM's here, the buses are set up like this. It kind of does this one thing in a certain way. Whereas on the mainframe, like you had mentioned several times now about the AI coprocessor. And I remember from the Linus video about the way in which the level 1 and level 2 cache is set up around these cores. It's very configurable. And then you have these massive buses that run between machines. And it's all of a sudden, one client could be and one workload could be I need to use that level 2 cache as level 3 cache in a different machine. And it would be it's faster to use it in a different rack than it would be even to reappropriate it within the same rack, given the workload. And so I don't know if I have a question here as much as I just went off on a rant and being super excited about it, but could you maybe delve into this a little bit and give us an understanding of how is this different and how is this architecture set up?
Yeah, the big thing, I think I touched upon it earlier, was just that since the whole intent of these machines is to do a lot of really fast data processing and manipulation, the cache system is so important to this chip. Even if you don't talk about the crypto coprocessor, if you don't talk about the AI accelerator, ignore all of that. Just as a chip, the caches are very big. And with the Z16 and the new Telum processor, they did an entire cache redesign, which is what you're talking about. And it's actually, it virtualized the L3 and the L4 cache, which is what can move around now and borrow from other areas. So the L2 cache, really fast, everything has access to it, and then it can change into different types of caches based on what the workload is doing. There is a really big article that gets into a ton of the hairy details of this. And I'll have to share that out too, because it's really fascinating. But it's actually a lot more than we could get into now. But it is definitely one of the strengths, for sure.
Yeah, and a lot of that is the processor takes care of it itself, right? So it's not setting up and configuring anything, right? It's you're configuring your memory access sizes, by LPAR, right, by virtual or logical partition, right? And then you kind of the processor assignment, and then all the cache is handling automatically under the covers. And it's doing exactly that, Luke. It knows like, hey, I could get to another drawer faster than reallocating, my local L2 to L3, right? And that's all done, by the millicode is the code that we call that actually kind of runs the processor. And that's all handled by that, right? So it's not like you have to click buttons and guess which ones and assign access. Nope, it's all handled via, your logical partition, access controls as to which memory it could touch, which drawers, right? And it happens under the covers.
Yeah, and we keep talking about drawers for the uninitiated. Drawers, so there's like 4 of them in like a fully loaded system, but you can just get one with one drawer. But a drawer, in this sense, is that it's just full of processors and memory. So if you find, I have an article out there about the hardware of the system, but the drawers look so cool, and you can also see it in the Linus Tech Tips video. Is like you see like I think there's like 40 RAM chips I think in each one of the drawers. Yeah.
So this is I got a little show and tell. So for those listening to the podcast, sorry, but I'll explain what I'm holding up. So this is a DCM dual chip module, right? And this is actually cut away. This is usually there's a heat plate here, but so you can see it. And what you're looking at, right, is the drawer is the processing unit. And on each DCM, you get 2 Telum processors, and every drawer we ship has 4 DCMs. So every drawer has 8 Telum processors. And yeah, you can buy 1, 2, 3, or 4 drawer configurations. And this is the heart of what makes it work, right? And like I said, you're getting, and you buy the drawers based on core count, right? Or the system based on core count, and then we populate the drawers based on that configuration. But each of the Telum processors has up to 16 cores, right? Minus spares, right? We have spares, and again, the goal is to make sure that, hey, if you have a core failure, within the drawer, we can move that workload, or turn on another core that's a spare, and it could be a core in a different drawer, and we know how to move that workload again to keep the customer from losing any capacity, right, and keep their workloads flowing. So it's pretty neat.
Something I want to highlight there, which I think you alluded to, was if you're building a traditional infrastructure system, you would be like, oh, I'm going to make a highly available pair. I'm going to have 2 systems, and I'm going to have some kind of fallover type scenario.
Yep.
Whereas like that's built in here, right? Like there is a massive amount of redundancy of everything, whether it's buses or processors or memory, and then it's hot swappable. So if something goes, you've already got the backup right there, and then whatever went, it probably doesn't happen very often, but if it did, you could actually just swap it right out while it's still running.
Yeah, absolutely. And like I said, it's core to our design principle. And one of the hardest things to do is actually, and take the example of a DCM where you had a number of core failures and you have to actually go replace the DCM. We could go replace one of these things while the system is running, right? We call it CDR, concurrent drawer repair, where we'll actually perform a service action. The system will remove all the workload that's running on that drawer and any of the IO cages it's attached to, right? Because we didn't talk about the IO. You could have up to 12 IO cages in a fully loaded system. Move all that work to the other drawers. Allow service rep to pull that drawer out, replace the DIMM, put it back. It could be a DIMM, could be DCM. Plug that thing back in, bring all that workload going, and run. And like I said, that is the hardest thing we do, and that's one of the things we pride ourselves on Z systems, is because there's no other system in the world that would even fathom doing that, right? While you're running mission critical workload, let's just go start replacing parts.
It's like changing your tire while you're driving down the highway or something.
Absolutely. And yeah, it's the thing, what makes it so hard is everything else has to work, right? All the system recovery, all servicing the whole network, right? Not just to mention the good workload running, the good path testing, but all that has to work, right? To even start thinking about trying to test that piece of the, and now it's basically you're starting again, making sure that happens, right? And we spend a lot of energy and effort, right? About, I would say 40% of our test plan is on recovery scenarios where we're injecting errors and faults on every component, making sure we can tolerate the fault, making sure we correctly report the fault, and then making sure we can replace that component. while the system is running, right? It's important, and it's like I said, it's the foundation of our system, and we got to make sure we spend the time, make sure it works, right? Because we want to make sure anyone who's running these things, has the confidence that we could go in and replace anything that fails. And if it fails, right, again, the system's not down; it's still running. Maybe you're running in a degraded state, but it's still running. We're going to go in, fix it, repair it, and bring it right back, and you won't notice the difference.
Yeah, that's wild. We're running out of time. We always use up our time so fast, but I'm doubling back on like getting involved in mainframes. And I'm also bringing back another viral thing. I'm reminded of the kid who bought a mainframe. I think he had to like even cut part of his house so he could get it into his basement. And then IBM, I think, even hired him after that for that. Yeah, what was that? 2016 or so. Anyway.
Yeah.
So there's another one, as of like this week. Another high school student, just bought what is it, the
Z14, I think.
But and he brought that in. I was like, oh my gosh, that's so cool.
Yeah.
You have like the coolest parents.
Yeah, right. There's another way to get involved. Go out there and buy a mainframe.
It's a good way to heat your house in the winter.
Yeah, right.
That's a good idea, actually. We could do some decentralized computing, and then you can heat your house.
Yeah. That's funny.
We have a comment here. Alex Kim, who actually looks like he had worked in Poughkeepsie and was an ex-mainframer. He said, love that story, PJ. It's the Dare to Unplug contest.
Yeah. No, absolutely. And like I said, and that was part of what Linus is like, can I just start ripping stuff out? And we're like, sure, that's what we're designed to do. Go do it now. Would I recommend, a bank start ripping cards out for fun? Absolutely not. But, and again, it shows the effort and the pride we have that we can just let somebody walk in and say, yeah, go for it. Go to town, right? Well, we could stand up to it. And it takes a lot of people, we talk like it's easy, but it is a lot of time and effort from the development side, architecture planning side, all the way through test and, delivery of that code out to the field with our running systems.
And I put the link up again, and I do recommend that folks watch this. And to reinforce what you said, PJ, you can see like his just deep knowledge of computing and the fact that he just learned about these systems, but he really was like, that's how the cache works. He was just like you could see, and his enthusiasm was like through the roof. He was very excited about getting to touch that stuff.
Yeah, it's a fun video. It's fun.
And it's great because, I get to play with that stuff every day. So, seeing somebody else come in and get excited, right? That makes it even more exciting for me, right? Because we don't have many opportunities of people just like, check out what we do and then understand it. And then like, be excited about it too. So it was definitely a great moment.
A lot of fun. Well, we are out of time. It goes so fast. But it's been really a pleasure to have you both on. Thank you all for tuning in and watching. And really, it's been a pleasure.
Thanks for having us.
Thank you.
Yeah,
cheers.
Thanks.